Welcome to lecture number 60th lecture, and we are trying to apply the graphical method in solving a circuit. So, this was a graph of the network, and we solve the circuit here for this circuit, and these are the 4 nodes present A, B, C, O, and we got last time we defined what the incidence matrix is. It may, you should not be under the impression why we are defining the A matrix like that. Okay, it turns out to be some matrix multiplied by the currents in various branches is essentially Kirchhoff's law, telling in that way, and its usefulness will be clear after some time. So, what we got is this thing, and I will say now after knowing the result, that is A into I E. I E is a column vector and this is equal to 0, and this is the reduced order, that is at O I am not writing the KCLs. How to got that result? We got it, we got this result, that is this result we got. This is the result we got, is not? Where let me cleanly write it now, reduced order A matrix as this. This will be your A. These are the entries. These 1, 2, 3, 4, 5, 6. See KCL at any node, there who will participate? Expected to be participated by any element currents. So, there may be 6 element currents I 1, I 2, I 3, and I fill up this, it is very easily seen. Okay. So, this is the one thing. Now, what I will be doing? Generally KCL we write while solving the networks by nodal analysis. When we want to solve the network by applying nodal analysis, we write down the KCL at different nodes. Now, let us see what is the size of this A matrix. This A matrix, what will be the size? You recall that E is the number of elements here. How many rows are there here? This is A, B, C. Okay. So, how many rows it will have? If there are 4 nodes, then the number of equations I am writing, reference node I am not writing KCL. So, it will be 1 less. So, if n equal to total number of nodes, total nodes, if that number is n, in this case it is 4, then KCL equations I will be writing only in 3 nodes, that is 1, 2, 3. So, the number of rows of this matrix in general will be n minus 1 into how many columns? Number of columns will be E, where E is equal to number of edges, So, it will be an n by minus 1 by E matrix, and this matrix, that is IE matrix, will be of course E by 1, it is a column matrix. On the right hand side you also have a column matrix E by 1, is not? This is the thing. Acha, now what I will do is this, Let me try to express the element voltages in terms of node voltages. Try to express the element voltages that is V1, V2, V3 etc. voltages by in terms of node voltages. What are the node voltages? VA0, VB0 and VC0. 0 is the reference node. So, it is very easily it can be seen that VE1, let me write down VE1, this element voltage is how much? VE1 is this voltage, this is plus, this is minus, is equal to VA0 over VE2, 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 the polarity you see, I will denote it by, depending upon this direction of the current, I am denoting it, it should be like that, plus minus, arrow is like this. So, VE2. So, VE2 will be V0B, which will be equal to minus VB0, is not V0B is minus VB0. So, VE2 will be negative of minus V0. So, VB0 is another node voltage. Similarly, VE3, which is straightforward, this is the direction of the current. So, VB0 minus VC0, VB0 minus VC0. Then in node 4, the voltage, element voltage existing across that branch VE4, it will be equal to VA0 minus VB0. Then in node 5, E5, it will be simply VC0, that is all, VC0. And finally, VE6, it will be VA0 minus VC0. So, we have been able to express the element voltages in terms of the node voltages V1, V2, V3 in terms of VA0, VB0, VC0. Now, this whole set of equations, 6 equations can also be written in a nice matrix form like this. I will write it like this: V1, V2, V3, VE4, VE5 and VE6. I will be able to write it like this. Here, who will be participating in this multiplication? Only 3 voltage participate, node voltages. This side I will write VA0, VB0 and VC0, is not? And here I will write also VA0, VB0 and VC0. This is no entry, just so that I will never be making mistake. So, VE1 is equal to VA0 only. So, I will put a 1 here and 0 0 there. VE2 is minus VB0. So, VE2 is minus VB0 is minus 1 0 0, no other, I am sorry, this can be written nicely like this. Similarly, voltage across element 3 V E 3, which is equal to V B 0 minus V C 0. So, V B 0 minus V C 0, V E 4, it will be V A 0 minus V B 0. So, V A 0 minus V B 0 minus 1 and 0. 5, E 5 is only V C 0. So, only 1 here 0 0, and finally, V E 6 is V A 0 minus V C 0 minus V C 0 0. In fact, one can straight away write, because for the first time you are doing. So, I wrote these equations and just translated it. So, it can be written in this way also. So, this is what I did, that is node voltages. In terms of node voltages, the element voltages can be expressed. Now, the question is, what is this matrix? Should I give it a different name? Now, it so happens this matrix is A. If you see this matrix is nothing but A transpose. See, first row 1 0 0 or 1 0 1 of A matrix has become the first column of this matrix 1 0 0 1 0 1. Similarly, second row 0 minus 1 1 minus 1 0 0, 0 minus 1 1 minus 1 0 0. Third row 0 0 minus 1 0 0 minus 1 has become the third column 0 1 minus 1. So, it is no new matrix. The relationship between element voltages and node voltages are like this. Acha, what will be, therefore, what will be the size? So, this matrix, these equations or can be written in a shorthand fashion as the element voltages is equal to A transpose, that is this one, into the node voltages. So, what is this vector? Column vector, column vector, which is this V A 0, V B 0, V C 0, 3 entries, because there are 3 nodes. Now, what will be the size of this V n? First, let us see the size of this A transpose matrix. Okay, A matrix was n minus 1 into A. So, it must be E by n minus 1, because A matrix size was this, its transpose. So, number of elements. This is the element voltage E minus 1. So, this size will be E into 1 column vector. This size will be n minus 1 into 1, and A transpose size will be E by n minus 1. Therefore, the incidence matrix which we got from the by writing down KCL equations also appears as A transpose, and it connects the element voltages with the node voltages. So, we say that reduced order A matrix. Henceforth, I will not even say reduced order A matrix, it is understood reduced order. What is the use of writing redundant equations? So, we have got the, in conclusion, it is like this: A into I E is equal to 0. Square brackets indicates it is a matrix, and also we have seen that A transpose into the node voltages, a column voltages, will give you the element voltages. This is the thing. This is where, see, I have now merely stated defined A matrix, and the entries of A matrix are very simple, 1, minus 1, plus 1, etc., plus 1 or minus 1, similarly of A transpose. And the fundamental relationship of element voltages and node voltages gave me this one, and simple application of KCL gave me this one. So, these are the statements. If you draw the graph of a network, directed graph, and then these two are shown, these two are correct. We will come to this further. See, I have not yet talked how to solve for currents and voltages. What merely I am telling is that there exists some matrix now A, whose entries are very simple numbers, plus 1 and minus 1, and they relate important things. Clear? So, we will now go to define another matrix, which is called cut set matrix. So, I will say this one. Cut set, not cut set, first let us tell tie set matrix. This is also very interesting, tie set matrix. What it is, I will tell you. And this will be relevant when you want to solve the circuit by nodal analysis. Is not, we write down the KCL. Somehow we know that if you know the node voltages, we have solved the circuit. Therefore, node voltage is involved, element voltages are involved, and then the KCL you have to write. So, by nodal analysis, only this point I note down here. By nodal analysis method, solving circuit by nodal analysis method, these equations to be used, only make a point to be used. Now, tie set matrix is B matrix. First, the last thing, it also, I know another method of solving a circuit. What it is? Loop method. Write down KVL at different loops of a circuit and try to solve for the loop currents and then the element currents. We know that. Therefore, in tie set matrix B, which I am going to discuss now, we will also yield two equations like this. Let us see first of all what this tie set matrix means. Now, you know that this always I will be needing. So, I will just copy this diagram, this one. This I will copy and paste it, next page, and put it here, because same network I have to talk in terms with. So, this is the thing. So, this was the tree of the network, This is how we have assigned the things. Now, given a network, we will say that we must now define what do I mean by a tree of a network. So, these are the keywords before I really start cut-set matrix. So, now this was the network, graph of the network. There were 4 nodes. I do not want to put all these variable names here to understand what a tree is of a graph. So, this is the graph of the network and it was directed graph. So, you can put the arrows like this, the way it has been assumed in the original circuit. This was the directions and these were the name of the elements. Simply write 1, 2, 3, 4 and where is 5? 5 and 6. This was the graph of the network. Now, note what a tree of this graph is. Tree of a graph we are discussing now, tree of a graph. First draw the nodes like this, then connect the nodes, suppose like this. So, all the branches I have not joined, same nodes are there A, B, C and this is O. Now, this will be called a tree of the graph. Tree of a graph is a structure like this, where all the nodes will be present and there will be no closed path. That is it. For example, this is I can call tree of the network, because all the nodes I have shown, something is connected to each of the nodes and no loop has been formed like this. Obviously, tree of a network is not a unique configuration like this, it is also a tree. If I have defined the tree like that, I will say this is also a tree. Because all the nodes are present A, B, C and O, but no closed form has been put. For example, one should not say that this is a tree of a network. All nodes are present, this is closed, this is not a tree, no, not a tree, not a tree. There should not be any closed path present, which is a subset of these elements. Some elements you choose such that all the nodes are present, no node is left alone, that is, this is also not a tree. Somebody says, draws like this and say that he draws like this, says that no closed loop is there, should I call it a tree? I will say no, because you have shown all the nodes, but this node is left out on its own, it cannot be also a tree. So, tree is a subset of the elements present in a graph in such a way that all the nodes will be there, nodes will be connected and there should not be any closed loop formed. That is it. I hope you have got the idea of a nodes, of a tree. Okay. So, this is a valid tree, this is also a valid tree. What I will be doing is, we will first take any tree you draw, okay? Whatever tree is possible, there are number of trees possible independent. For example, this is also a tree, let me draw. This is also a tree, this and this is also a tree, is not? No closed loop is there, all the nodes are present. Choose any one of them you like. So, I have chosen this to be the tree for ongoing discussions now about this, what should I do with this tree. And since it is a directed graph, also show its direction and the element name whatever you have given, try to maintain that. So, this is 1, this is element 2, this is element 3. Now, the question is how many elements will be present in a tree? If total number of edges is E here, how many elements will be present in a tree? Number of elements which will be present in a tree, if the number of nodes are n, is n minus 1. You see it, there are 4 nodes, 3 branches will be present. Now, when it comes to tree, it consists of also branches or edges. These edges are given a separate name called twigs. Number of twigs is equal to n minus 1. In this case, it will be 3. Got the idea? And it is denoted by this letter T. T is not time, number of twigs present in this one. Acha. Now, the left out branches which are not shown in a twigs, I am showing them by some dotted line with red colors. These are the edges I have omitted to construct this tree of this network. These are another 3 were there. Na? So, these are the 6, total number of branches were 6. So, these 3 red lines I have shown with dotted things, these are called links. So, this is tree and this red one is called co-tree. So, these are some definitions with which you will be very much familiar soon after you practice a little bit. So, graph was a full thing, directed graph, all the elements you are showing. Now, I am telling you tree is a collection of these edges showing all the nodes here in such a way that they should not form a loop, that is the blue one only. How many elements will be there in a tree? It will be n minus 1 over. The left out branches to construct the tree is these red lines. This I will call co-tree, I will call it co-tree. And the branches of a co-tree are called links. So, I write it, branches of a co-tree are called links. Then branches of a tree or edges of a tree are called twigs. How many twigs will be there? N minus 1. How many links will be there? Oh, total number of edges is E. Therefore, subtract E n minus 1 from E. That will also tell you how many edges will be there. Or so, these are the statement of this. In the full graph, I will say branches or edges, total number of edges I know, what are the things I know, total number of nodes I know. Then I construct a tree, the elements or edges which will form a tree, they are given a name twigs, number of twigs will be n minus 1, and the left out branches which I have not eliminated, I have discarded while constructing the tree are shown by these dotted red lines. These structure is called a cotree, this red portion only with this blue erased, that is called a cotree. Cotree plus tree is your original graph if you make all things farm line. And the question is how many links will be there? Number of links. Those branches of a cotree I will call links, and number of links will be E minus n minus 1. We will continue with this in the next class. Please, this is an interesting topic. Please go through it, very logical and very interesting too. Thank you.